Imagine the ocean on a scorching summer day, the air shimmering with heat and the horizon stretching endlessly. The sun beats down, warming the water like a giant bath, raising the temperature of the sea until it feels almost tropical. As the water heats up, it evaporates, sending warm, moist air rising high into the sky. This air cools and condenses, forming towering clouds and releasing huge amounts of energy into the atmosphere. This released energy is what gives birth to a hurricane, a massive swirling storm system that acts as nature's way of moving heat from the tropics toward the poles, balancing the planet's temperature. Hurricanes are colossal engines of wind and rain, powered by the endless supply of warm ocean water and the constant rising of moist air. They can stretch hundreds of miles across, with winds that roar and rain that pours relentlessly. But hurricanes don't form just anywhere. They need very specific conditions. A sea surface that's at least 26 degrees Celsius, humid air above the ocean, and a weather disturbance to kick things off. When all these ingredients come together, the system begins to spin, fueled by the Earth's rotation, and a calm, almost eerie eye forms at its center, surrounded by the storm's fiercest winds. To help track and communicate the threat of these powerful storms, each hurricane is given a name, making it easier for people to follow updates and prepare. A tropical storm officially becomes a hurricane when its winds exceed 74 miles per hour, strong enough to bend palm trees and cause serious damage. Hurricanes travel across vast oceans, sometimes for days, battering coastlines with huge waves and heavy rain, reshaping beaches and impacting entire communities in their path. Even after their initial fury fades, hurricanes don't simply disappear. They can continue their journey, sometimes reaching as far as the UK, bringing wind and rain to distant shores. Though their roar may fade, the influence of hurricanes lingers on, affecting weather patterns and leaving a mark far from where they first began. Let's focus on Hurricane Melissa, born in October 2019 in the Central Atlantic. It was a late-season storm, a reminder of nature's unpredictability. Melissa reached hurricane strength but stayed at sea, a Category 1 hurricane. It was a fascinating system for meteorologists to observe. As it moved north, it traveled over colder water, losing its warm core. This transformation is called extratropical transition. The storm stops being a tropical cyclone and becomes extratropical. It no longer draws energy from the ocean, but from temperature contrasts in the air. Hurricane Melissa underwent this process, losing its hurricane status. It entered a new chapter, still carrying moisture and energy from the tropics. This transformation is crucial in understanding how these storms evolve. When a storm like Melissa becomes extratropical, it undergoes a dramatic transformation, shifting both in structure and behavior. It moves northward into the mid-latitudes, where the UK sits, tapping into the sharp temperature differences between warm and cold air masses. The storm gradually loses its iconic eye and the tight, symmetrical structure that once defined it as a hurricane. Now, the strongest winds are no longer concentrated at the center, but spread out over a much larger area, and rainfall becomes more widespread, soaking vast regions. It starts to resemble the low-pressure systems that are so familiar in the UK, blending in with the typical autumn and winter storms. The ex-hurricane is eventually absorbed into the larger weather pattern, merging with other systems and losing its individual identity. Yet, it still carries a plume of moisture and energy from its tropical origins. bringing a touch of the tropics to northern skies. The UK doesn't experience a hurricane's fury, but instead faces the remnants, the ghost of the storm, manifesting as persistent rain and gusty winds. The storm has changed form, now existing as a sprawling, diffuse area of low pressure, stretching across hundreds of miles. Its journey across the North Atlantic is guided by the powerful jet stream, steering it toward Europe and shaping its path. In the end, the storm's legacy is not its destructive power, but the moisture it brings, subtly influencing the weather and leaving behind days of drizzle and grey skies. Once Melissa became an extratropical storm, it was swept up by the powerful jet stream, a fast-moving current of air high above the Earth's surface. This marked the beginning of a remarkable journey across the vast Atlantic Ocean. This high-altitude river of air acted like a conveyor belt, steering Melissa steadily eastward, guiding it thousands of miles from its birthplace. As it travelled, the storm system evolved, merging with other weather features and picking up new characteristics along the way, becoming part of a larger, more complex system. Although Melissa was no longer generating energy from the warm ocean waters, it remained a significant presence in the atmosphere, its swirling clouds still visible from space. As it continued east, Melissa joined the busy weather traffic that constantly moves across the Atlantic, a procession of systems shaping the weather for entire continents. The storm carried with it a plume of warm, humid air from the tropics, transporting moisture and heat far from its original source. By the time Melissa approached the shores of Europe, it was no longer a raging storm, but its influence could still be felt in the changing skies. Instead of fierce winds, it brought moisture, like a giant, invisible sponge drifting across the ocean, subtly altering the weather wherever it went. Melissa's journey is a powerful reminder of the interconnectedness of global weather, where a single storm can ripple across continents and oceans. A storm forming off the coast of America can eventually influence the weather in the UK, demonstrating how distant events can have local impacts. Melissa's voyage was a quiet migration of air and water, a distant echo of its former self, but still a vital part of the planet's ever-changing weather story. When Melissa's remnants reached the UK, they didn't arrive with a bang. The impact was subtle, influencing rainfall rather than causing storms. The tropical moisture fed into existing weather systems, enhancing them. Normal weather became juicier with heavier, more persistent rain. The UK didn't experience a hurricane, but felt its legacy. The moisture-laden air was lifted by hills, forming rain clouds. The result was unusually damp weather, not stormy or windy. For most, it felt like a typical rainy spell, not linked to a distant hurricane. This is the quiet nature of extratropical systems, whispering their presence. Imagine the atmosphere as having invisible rivers of moisture. Normally, these rivers bring typical weather to the UK. An extratropical storm diverts a larger, warmer river from the tropics. This tropical river holds more water vapour than usual. When it flows over the UK, it increases available moisture. Existing weather systems tap into this enhanced supply. Rainfall becomes more intense and prolonged. The concept of atmospheric rivers helps visualize moisture transport. Melissa's remnants created a textbook example of this. It was a conveyor belt for water, delivering tropical humidity to the UK. The UK didn't experience a hurricane with Melissa's remnants. It was a few days of dreary, wet weather, not dramatic. The impact varied across the country, with western areas receiving more rain. The moisture-laden air rose over high ground, squeezing out rain. Rainfall totals were above average, but not destructive. Eastern areas experienced less pronounced effects. The storm's impact was a rainfall event, not a wind event. Melissa was a classic example of a subtle extratropical system. Its legacy was dampness, not destruction. It reminded us of our weather's global connections. Understanding these connections is crucial for weather forecasting. Tracking extratropical systems improves predictions of heavy rainfall. This advance warning is vital for farmers, emergency services, and planning. These events are part of our water cycle, replenishing reservoirs and rivers. They help us manage water resources and prepare for future challenges. Studying these distant echoes deepens our appreciation of global weather. The atmosphere is interconnected, influencing local weather. The journey of a storm like Melissa illustrates this complexity. It shows the subtlety of weather impacts and global connections. As the climate changes, storms like Melissa become more relevant. Warmer oceans could make tropical storms more intense. Stronger storms carry more energy and moisture across the Atlantic. This could make distant echoes more pronounced in the UK. Preparing for these changes is crucial for resilience to flooding. Understanding Melissa's journey helps us prepare for the future. It illustrates the subtlety and complexity of weather impacts. Nature's quiet, long-distance connections teach us about global weather. By understanding these connections, we can better prepare for the future.